Rates of change in the natural and social sciences. What is rate of change? Average rate of change can be represented by the difference quotient, which is the change in y over the change in x. As the change in x approaches 0, this becomes the derivative f prime of x. This is the instantaneous rate of change of y with respect to x, as shown in the equation here. So how does this look graphically? The red line represents the secant line, which is the average rate of change between points at x equals 1 and x equals 4 for this graph. The green line represents the tangent line at x equals 2, which is the instantaneous rate of change at that point. So how does this apply to the natural and social sciences? The basic idea of rate of change can be applied to many areas within the natural and social sciences. The key to solving rate of change problems is to interpret the question by finding what is changing and how to represent that change with an equation. So physics. Physics is a common natural science that rates of change frequently apply to. First, you need to know a little bit of background for physics. There are three main functions, which are position, S of t, velocity, v of t, and acceleration, a of t. Velocity is the average change in position over time, and acceleration is the average change in velocity over time. With instantaneous rate of change ideas, the following equations are true. A of t is equal to the derivative of v of t, which is equal to the second derivative of s of t. Additionally, here are some common things that you need to know in order to solve physics problems. At rest means that v of t equals 0. Velocity is positive means that the particle is moving right or up, and velocity is negative means that the particle is moving left or down. Acceleration is positive means that velocity is increasing, and acceleration is negative means velocity is decreasing. If signs of velocity and acceleration are the same, the object is speeding up. If signs are opposite, the object is slowing down. So here's a physics example problem. The position of a particle is given by the equation s of t equals t cubed minus 9t squared plus 24t. So we're going to try to find a lot of things here. Let's jump right in. We're going to first find a, the velocity and acceleration functions. Velocity function is simply the derivative of the position function. We're going to get 3t squared minus 18t plus 24 for the velocity function. And then for the acceleration function, we're going to find the derivative of the velocity function, which is then going to be 6t minus 18. This is all done using simple power rules. Part B, the times at which the particle is at rest. Times at which the particle is at rest is when v of t equals 0. So we're going to set the velocity function equal to 0 and solve. We're going to factor out 3, and we're going to factor out things to make it visually pleasing, and we're going to get 3 times t minus 2 times t minus 4, which we're then going to get the particle is at rest when t equals 2 and t equals 4. This is an important statement you need to include after you solve the question. It's commonly mistaken. People forget to put this sentence, but you need to include the statement in order to indicate what you have found. Part C, the times at which the particle is moving to the right and to the left. So v of t is positive when the velocity function is greater than 0, which is true when both factors are positive and both are negative. V of t is negative when the velocity function is less than 0, which is true when one factor is negative and the other is positive. So the particle is moving to the right when t is less than 2 and when t is greater than 4. And the particle is moving to the left on in between t equals 2 and t equals 4. Part D, the total distance traveled in the first 6 seconds. S of t equals t cubed minus 9t squared plus 24t, as originally stated. So we're going to first plug in 0 to that equation, and of course you get 0. S of 2 is 20, S of 4 is 16, and S of 6 is 36. So in order to find the total distance traveled in the first 6 seconds, we need to find from the final spot to the initial spot at each of those spots. So what we're going to do, we're going to do 20 minus 0, 16 minus 20, and 36 minus 16. But the 16 minus 20, common mistake, people believe that that's a -4, but it's not. It's a +4 because that's included as total distance traveled. So we find the absolute value of that difference for a total distance traveled in the first 6 seconds by the particle for 44 units. Now the time at which the particle is speeding up or slowing down, a of t is equal to 0 at t equals 3. So that's when acceleration changes from negative to positive. So we're going to analyze when velocity and acceleration are positive and negative. As you can see in the chart, velocity and acceleration change from positive to negative at various times. Now, through the chart, we're going to be able to say that the particle is speeding up on t equals 2 to t equals 3 and t equals 4 to t equals infinity, and the particle is slowing down before t equals 2 and in between t equals 3 and t equals 4. We're able to determine that by looking at the signs in our chart to determine when it's speeding up and slowing down. This is a common mistake here, that people think that positive velocity simply means that it's speeding up, but no, you need to go through this entire process here. So economics, the basic idea of the derivative and rates of change, can also be applied to economics and business. Cost, profit, and revenue are common areas of economics that rates of change can be applied to. You should be aware that profit equals revenue minus costs. And marginal whatever is whatever from producing one more item. So that could be cost. Marginal cost is the cost from producing one more item. So we're going to get into an example problem here. So the production cost per week for producing X balls is given by C of X equals 300 plus 500X minus 0.08 times X squared. So we're going to try to find the cost of producing the 95th ball and the rate of change of the cost at x equals 94. So first, we're going to find the cost of producing the 95th ball. This is the cost of producing 95 balls minus the cost of producing 94 balls. So you simply do C of 95 minus C of 94, which we're going to get is $484.90. So the cost of producing the 95th ball is $484.90. So some people simply plug in 95 to the C of X cost function formula and believe that that's the cost of producing the 95th ball. No, it's not. That's the cost of producing 95 balls total. But in order to find the cost of producing simply the 95th ball, you need to do the process that we just did. Now for part B, the rate of change of the cost at x equals 94. You should recognize that this means the instantaneous rate of change at x equals 94, which requires you to compute the derivative of the cost function. The derivative of the cost function is 500 minus 0.16x. Then we're going to plug in 94 there. We're going to get 500 minus 0.16 times 94, which is $484.96 per ball at x equals 94. So what did we learn from that? We learned that marginal whatever, in this case marginal cost, is not only the cost to produce one additional item, but also approximately the rate at which blank whatever it is, in this case cost, is changing. Therefore, the marginal cost function or marginal whatever function can be written as the derivative of the cost function or the derivative of the whatever function. So, as learned, there are many applications of the derivative and rates of change to the world. But remember, the key to solving these problems is to determine what is changing, how to represent the change with an equation, and determining what variables to plug into the equation. Good luck.